last but not least presentation is by Aaron Forde, whom I want to come up. And I do not have steam to give long introduction, but in some sense he will teach us how to violate energy conservation law.
That's a pretty big prelude you give. Where am I on here?
Diagonal. See this diagonal?
Oh, there's the diagonal.
Yeah. Yes.
There we go. Okay, so I'll be speaking about the 5th chapter that we covered in the class, which we covered motivation for of how relaxation happens due to a noisy bath, conditions for thermal equilibrium. I didn't explicitly talk quantum versus classical bath. I focus more on quantum, so I look forward to some hard questions on that. Some microscopic theory behind the quantum heat bath. The tools that we use to describe the time evolution of the system, some commutation relations, and how population relaxation actually works. So, my intro slide, dynamics. So we have a 2-level quantum system coupled to an ensemble of quantum harmonic oscillators. So on the top of the screen we have N harmonic oscillators, which are, I tried to approximate as parabolas that all have energy populations that can be occupied. And then we couple this ensemble to a 2-level state where state A is the ground, we define as the ground state, and B is the excited state, and then gamma represents the transition between those states, and then N represents the phonon modes, which we'll see how those are the average of quanta from the phonon modes, which we'll see at the end of the presentation. So who needs this tool for modeling? So basically, whenever you're trying to model the dynamics of some system that's in a big noisy bath, or the bath where it's basically inherently random, and then you can model everything as fluctuations that happen within the bath. So things that systems that you'd want to track the evolution of would be like electron spin states, how the noisy bath would influence the orientation of spins, or for photoexcitations, how the noisy bath affects the transitions between after your photoexcitation, how it evolves. And then you could also do like ions and solvents, so where you have a lot of water molecules constantly hitting your ion. So that could be pictorially described as we have our system that's surrounded by a big bath, and then we have something that pokes the system and perturbs it, that creates it, takes out of equilibrium. And then to get back into equilibrium, we have arrows representing the energy flow outside of the bath. And then I specifically noted that even though it is an open system, there's nothing from the bath going into the system, because we assume that the bath is always in equilibrium, so there's no need for energy to go into the system from the bath. So the main mathematical tool that we use to describe the time evolution of the density matrix is the reduced density operator. So for the top equation, it represents the density matrix that Deanne described earlier, and then this part specifically is the second order perturbative expansion of the density matrix, where the 0th order, it depends on initial conditions, so we just set that to 0. And then the 0th order depends on initial conditions, so we just set that to 0. The first order depends, it basically averages out at the end of the calculation, so we just ignore that. So the most significant term that we focus on is the second, so that's why we leave that. It has a double commuter between two different interactions, and then
commutator.
What did I say?
Commutator.
Yes. It depends on two different potentials at different time intervals, and then our density. So we start with describing the time evolution of the system and the bath, but we only really care about the system, so we only care about how the bath acts onto the system. So to describe just the system part, we take the trace, which is basically just turning all the elements from the bath into numbers. And then we use a trace operation, so we describe only the time evolution of the bath. So basically the trace operation just goes on the inside of the integral. So basically the only two things that we have to figure out for this equation is the form that we want our potentials to be, and then the form of our density matrix. There should be a bath on there too, so it trace over the system and the bath. So for our system and the bath, we assume there's no correlation at any time between the system and the bath, so we just say that they're products of each other. And then we know that we're coupling harmonic oscillators, so we use, for our bath, we make it products of all the harmonic modes, or the density of all the harmonic modes, which is basically the dyadic product of each of the harmonic states times the probability of occupations for each state as you go up the ladder of the harmonic oscillator, which is represented by n. And then for our interactions, we assume that there's no correlation between the system and the bath operators, but that they act independently, so they're products. And then for the system, this represents the mixing of two different states due to the motion of ions. And then for the bath, we just use the momentum operator, which in the language of ladder operators is represented as the minus of the lowering operator of the plus operator. And then those are explicitly noted here. And then we have two different modes that we're summing over, so K, because of the commuter, for the double commutations. So we do go over K and K prime. So that's those notations stand for. So basically we've set up the problem, and if you want to go through the nitty-gritty details, there's an hour and 40-minute video on YouTube that goes through all the mathematical steps. But basically what we get from doing all these steps is we get transition rates due to the coupling of the states and the autocorrelations of the baths. We also get due to, well, I guess we'll go to the next slide. So those give us our rates. And then the n's represent the average number of quanta from the harmonic oscillators. So and then we get n's and n plus 1s, and those come from the commutation relations. And yeah, then we also get expectation values from the reduced density matrix, where they're convoluted with the ground state and the excited state. And then if we assume a steady state solution, so that our time derivatives are 0, so that there's no changes in the occupations of the state, we basically, if this is 0, we can solve the equation so we get ratios of the excited state over the populated state. So that turns out to be n over n plus 1, which turns out to be a Boltzmann factor. So that essentially tells us that the transition from A to B is a Boltzmann factor less likely than from B to A, or it's more likely to go from excited to ground state than from ground state to excited state. So then these are just some illustrations from labs that we did. So if we assume that there's 0 temperature so that none of the harmonic modes are oscillated, or that none of the harmonic oscillators are filled at all, so basically it's just, there's no thermal motion to couple with the electronic states. So if we assume initial conditions where everything's in the ground state, we're going to get 0 because we put 0 in the denominator of the exponential. That's going to make it e to the negative infinity, which basically gets 0. So we're always going to be in our steady state will always be in the, or our equilibrium state will be fully populated in the ground state and none in the excited state. And then after, if we do a pi pulse, even after the transition, it will eventually go back into the ground state. And then if we have a finite temperature, and then our initial condition is fully populated in the ground state, it will eventually equilibrium to a steady state, which defines equilibrium for this case. And if we just put a finite number in for our KT, we'll get some sort of number in between 0 and 1. So our equilibrium state will be some proportion of like 80% in the ground state and 20% in the excited state. And then if we put in infinite energy into the system, basically, well, if we put infinity into our Boltzmann factor, we'll get a ratio of 1. So that assumes that the ground state and the excited state will be equal, or they'll have equal populations. And even if we try to drive it out of the excited state, there's an infinite energy keeping it into this steady state solution, so it's not going to move.
Okay, let's thank Aaron. And